Today we are going to discuss about Grashof's criteria. Okay, let's consider a 4-bar mechanism. In this 4-bar mechanism, or in general, in any mechanism, we will give an input which is in the form of motion and an output which is in the form of a motion again, but in a different form. Okay. So in a 4-bar mechanism, the output will be mostly the output will be in the oscillatory form, and the input will be either in the oscillatory form or in a complete rotary form. Okay, a complete rotation or a continuous rotation. Okay, so among these two inputs, the complete rotation is preferred. The reason that's been preferred is because say I could give the input using a motor. So I can do that by fixing a motor with this fixed frame and connecting the shaft of that motor to this link so that it can have a complete rotation, and continuously it can have a rotation with respect to the fixed frame. Okay, and therefore it would be nice if we have a mechanism which could receive a complete rotation as an input and give the desired output. Okay, but now the question is, can we have all the 4-bar mechanism to have a complete rotation? The answer is no. Okay, let's see an example. So in this in this example, let me play this animation for you. See, this link does not providing a complete rotation, right? So let me yes, it's not giving complete rotation. So once it reaches this configuration, okay, these link lengths are not letting this link to go further in this direction. Okay, same goes for this configuration as well. It cannot, this link cannot go further in this direction. Okay, so so this mechanism, in this mechanism, we cannot have this link to have a complete rotation, and the same goes for this link as well. If we see, yeah, now this link cannot go further in this direction. Okay, so there is some limitation in this linkage. At the same time, if we see this mechanism, this link is having a complete rotation, so that I could give a continuous rotation as an input. Okay, so now this is also a 4-bar mechanism, and this is also a 4-bar mechanism, right? But among these two mechanisms, how can I say that whether a mechanism can have a complete rotation? Okay, so what is the condition? That condition is given by Grashof. Okay, so what is this Grashof's criteria? So let's say this is this link name is L1, and this is L2, and this is L3, and this is L4. Okay, the angle between L1 and L2 is theta 1, and the angle between L2 and L3 is theta 2. Okay, so now in order to have this link L2 to have a complete rotation, it has to satisfy two conditions, which means those conditions are theta 1 has to be 0. At theta 1 is 0, the configuration should exist, and theta 1 should also be 180. For theta 1 equal to 180, the configuration should also exist. Okay, if these two extreme conditions are satisfied, then I can say that L2 will have a complete rotation related to L1. Okay, but in order to have a complete rotation as a mechanism or as a kinematic chain, then these two conditions are not enough. Okay, this angle, which is theta 2, should also satisfy these two conditions. Okay, and if we make sure that these conditions are satisfied, then I can say that that particular mechanism will have a complete rotation. Okay, now let's try to impose this condition. So if this condition is satisfied in the mechanism, what does that mean? When theta 1 is 180 degree, which means this angle is 180 degree, then these 3 points come into collinear. If that's collinear, then this form a triangle, and then I can use triangular inequality. So by imposing the triangular inequality, I can obtain this inequality equation. Okay, and then I'm going to use this condition. By imposing this condition, I will have this triangle, and again I am going to use the triangular inequality for this triangle, which will give me these two inequality equations. Using these three inequality equations, I could obtain these three relations. Okay, and if we see these three relations, we could see that L2 has to be the smallest among all the links, right? So therefore, what I'm going to do is, in the place of L2, I'm going to replace that L2 with S. Okay, so just to represent, that's the smallest. Now among the three, L1, L3 and L4, I'm just going to assume any one of the link as the largest. Okay, so for the sake of illustration, I am going to assume L1 as the largest. Okay, so why L1 is largest? It doesn't matter, because these three equations are symmetry. If I replace any two links, then I will again obtain the same set of equations. Okay, so if I assume L1 as the largest, then using this inequality condition, I will obtain a relation that the length of the smallest plus the length of the largest should be less than or equal to the length of remaining two links. Okay, so that's the condition, and that condition, by imposing that condition, I can make sure that these two conditions are satisfied. But I haven't discussed about these two conditions, right? But it doesn't matter, because if I consider these two conditions, then once again I will obtain the inequalities which are the same three equations. Okay, these two equations as well as this equation. So it doesn't matter, just by imposing these two conditions, I automatically satisfy these two conditions. I leave that as an exercise. Okay, so in order to satisfy all these conditions, all I have to do is I have to make sure that this inequality is being satisfied, and this is known as Grashof's criteria. Thank you.